Welcome back, everybody. I'm here in part 3 of the Chapter 12 lecture note outline packet. And the last time we discussed saturation. So we talked about unsaturated, saturated, and supersaturated situations with solutions. Today we're going to first start off by looking at the effect of different parameters like temperature and pressure on solubility. And then we'll get into some work with units of concentration. So let's talk about this effect of temperature first on solubility. So I have this graph down here below that shows the solubility of various solutes in water at different temperatures. So you might notice a trend here that as we increase the temperature, we also increase the solubility of most solutes. So for example, if we look at potassium nitrate, we see that down at 10 degrees Celsius, there's a solubility of about 20 grams of potassium nitrate, the solute, in 100 grams of water. Now, if we raise the temperature of the water to about 50 degrees Celsius, the solubility increases dramatically. Now, 90 grams of potassium nitrate can dissolve in the same amount of water. Also notice this is not always true. Sometimes the solubility actually decreases as we increase the temperature of the solution. For example, let's look at the solute cerium sulfate. The solubility of cerium sulfate at 10 degrees Celsius is about 10 grams in 100 grams of water. Notice, however, that at about 50 degrees Celsius, the solubility has decreased by more than half. So maybe it's something like 3 or 4 grams of cerium sulfate at 50 degrees Celsius will dissolve in 100 grams of water. Now, why are these two salts behaving differently? Why, when we raise the temperature of one, we increase its solubility, but the other one decreases? Well, it turns out to have to do with the different way that potassium nitrate dissolves in water versus cerium sulfate. When potassium nitrate dissolves in water, it actually absorbs heat from the surroundings to help it dissolve. This is why increasing the temperature makes it dissolve more. Cerium sulfate, on the other hand, releases heat as it dissolves in water. Having additional heat around interferes with this process. In fact, the best way to help cerium sulfate dissolve is to remove heat rather than add it. This is why the solubility of cerium sulfate increases as you decrease the temperature. Now we'll go over that concept in quite a bit more detail a little bit later in the course. For now, just note that for most solutes, an increase in the temperature leads to an increase in the solubility of that solute. Now let's go to the next page where we will look at the effect of temperature on the solubility of a gas in a liquid. Now, as you know from our study of gases, increasing the temperature of a gas increases the average kinetic energy of the molecules which comprise the gas. When we increase their average kinetic energy, what we're doing is increasing their movement. And as a result of this, we're decreasing their solubility in a liquid. Here's a graph as an example which shows several gases including nitrogen oxide, oxygen gas, carbon dioxide, methane, and nitrogen. We see that for all of these gases, the solubility decreases as the temperature increases. So, unlike solids dissolving in liquids, gases are consistent. Their solubilities always decrease as the temperature increases. We should also consider the effect of pressure on the solubility of liquids and gases. Now, for solids dissolving in liquids, there is very little effect from increases or decreases in pressure because liquids and solids are inherently not very compressible. So increasing the pressure doesn't have much of an effect on these. Now, gases, we know, are very susceptible to changes in pressure. Increasing the pressure decreases the volume of a gas, and decreasing the pressure increases the volume of a gas. So as I'm showing in this diagram, when we decrease the volume of a gas, we're increasing the solubility of the gas in the liquid. That's because we are increasing the amount of collisions per the same amount of surface area. And that increased number of collisions leads to an equilibrium in which more of the gas is dissolved in the liquid than in the gas phase. So we can summarize this as saying that an increase in pressure leads to an increase in the solubility of a gas. Why is this? Because when we increase the pressure, we are decreasing the volume of the gas. And naturally, this leads to an increase in the number of dissolved particles. So now that we've had a chance to discuss some different aspects around solubility and the effects of temperature and pressure on solubility, let's go to the next page where we can learn how to quantify solubility through concentration. So here in part 4 of the chapter 12 lecture notes, we're going to start talking about concentration. Concentration is a measure of the quantity of a solute that is dissolved in a solution. There are several ways to do this, and we will learn 3 of them. We'll learn about percent by mass, percent by volume, and molarity. Let's start with percent by mass. When we express concentration using percent by mass, what we're doing is we're showing the percentage of mass of a solute that is dissolved in the total mass of the solution. We can find percent by mass by taking the mass of the solute and dividing it by the mass of the solution, and then multiplying that by 100. This will give us a percentage. Remember that when we find the mass of a solution, we have to include the mass of the solvent and the solute. So let's apply this to an example. This example says, what is the percent by mass of a 0.500 gram sodium chloride solution in 100 milliliters of warm water? The warm water has a density of 0.985 grams per milliliter. When 2 liquids are mixed together, it's possible to express the concentration of one liquid in the entire solution as a percent by volume. Percent by volume is found by dividing the solute volume by the total volume of the solution which is formed when the 2 liquids are mixed. So we would take the volume of one of the liquids and we would divide it by the total volume of all of the liquids mixed together, and then we would multiply that result by 100 to give a percentage. So as an example, we have what is the percent by volume of a 20 milliliter hexane solution that is prepared, and the total volume comes out to 503 milliliters. To find the percent by volume of hexanes in the solution, we would take 20 milliliters for hexanes and divide it by the 503 milliliters. That's the total volume of the solution, and then we would multiply this result by 100 to give us the percentage, which is 3.98% by volume. Now, there's one additional way that we often use to express concentration, and it's not based on the mass or the volumes of the components in the mixture. It's actually based on the number of moles that are dissolved. This method of expressing concentration in terms of moles is known as molarity. Specifically, molarity, which we give the symbol capital M to, is an expression of the concentration where the moles of the solute are specified for every liter of the solution. So for example, if we said something was 2.5 capital M, what we're saying is that that solution is 2.5 molar, or has a 2.5 molarity. And if we're talking about sodium chloride, what this refers to is if we had a 2.5 molarity solution of sodium chloride, it would have 2.5 moles of sodium chloride for each liter. So for instance, what if we had 2 liters? Well, that would mean we would have 5 moles of sodium chloride. So molarity, which we use the capital M to represent, means the moles per liter of a solution. And it's also helpful to remember that 1 liter is equal to 1,000 milliliters. So we can also say that molarity means moles per 1,000 milliliters. So to see how this works, let's try out an example. What is the molarity of 12.3 grams of sodium hydroxide are dissolved in water to give a solution that is 789 milliliters? So to calculate the molarity, we need two things. We need the moles of the solute, and we need the volume of the solution. Notice that we're given the grams of the solute, and if we want to convert that into moles of solute, we need to use the molar mass. So let's do that first. So I start with the mass of the solute, that's 12.3 grams of sodium hydroxide, and then I multiply it by the conversion factor that is moles per gram. Again, that's molar mass. So basically I'm taking 12.3 and I'm dividing it by 40 grams. That gives me 0.308 moles of sodium hydroxide. Now I just need to find the volume of the solution. Now we're given the volume as 789 in the units of milliliters. We need to make sure we're converting that into liters before we can compute the actual molarity. To convert milliliters into liters, I divide by 1,000 milliliters. So we get 0.789 liters as the volume of the solution. Now I can go ahead and calculate the molarity. I divide our moles of solute by the volume in liters of the solution. So it's 0.308 moles divided by 0.789 liters. I get 0.390 moles per liter this way. We can rewrite this as 0.390 with a capital M there, because moles per liter equals molarity. These are one and the same. But it's okay to also write moles per liter as well. So now that we know how to find the molarity, let's also see another way that we can use it to calculate different types of quantities. So in this example, we're looking for the mass. So let's read through it. It says how many grams of HCl would be present in a 50 milliliter aqueous solution that has a molarity of 0.250. So to understand how to do this, it's really helpful to have a good understanding of really what molarity is. Molarity, of course, is a unit of concentration, but more than that, it's a conversion factor. It's a conversion factor between moles and volume, specifically liters or 1,000 milliliters. So if we have molarity, we can convert between moles and volume, or volume and moles. So let's look at the different values that we're given in this problem. We're given the volume in milliliters, the molarity, that's moles per liter, and we're being asked for the grams of HCl. So the way we're going to solve this is we're going to convert volume into moles first. And how do we do that? Well, that's right, we're going to use the molarity, because that's the conversion factor between volume and moles. And once we have the moles of the solute, we can convert that into its mass by using the molar mass. So let's see how to set this up. We have two steps, and our starting point is 50 milliliters. So let's write down that 50 milliliters and then do the first step where we're going from milliliters into moles. Once we have moles, we'll turn that into grams. So the first conversion factor where we're converting volume into moles is molarity. And the second conversion factor where we're converting moles into mass is the molar mass of HCl. So let's plug the values in for each of these conversion factors. We have the molarity is 0.250 moles, and that's per 1,000 milliliters, so that those units cancel. Our molar mass is 36.46 grams per mole, so that moles cancels. And then when we plug this into our calculator, we get 0.456 grams of HCl. So if you can, try to think of molarity as a conversion factor, right? It's a ratio between moles and liters or moles and 1,000 milliliters, so it lets us convert between those two units. So let's go to the next page where we'll learn one more way we can use molarity, and then we'll learn about something called dilution calculations. So here on the next page, we start off with another example of molarity. And I want you to give this one a try for yourself to see how it works and see how you do with it. Let's read through it together, and then I want you to pause the video and give it a try. It It says how many grams of sodium bicarbonate would be needed to prepare a 30 milliliter sample with a 0.355 molarity concentration. So go ahead, pause the video, and see how you do with this one. Now, if you're stuck on this one, here's a little hint. Notice the values you're given. You're given 30 milliliters and you're given molarity. Now, which one of those looks like a starting point and which one of those is a conversion factor? Well, that's right. The volume, 30 milliliters, is your starting point, and your conversion factor is molarity. So with that, give it a try. So the solution to this involves taking the volume, converting it first into moles using the molarity, and then we convert moles into mass using the molar mass. So my first conversion factor is molarity, and I write down 0.355 moles. That's per 1,000 milliliters. I've chosen 1,000 milliliters there so that I don't have to first convert that 30 mils into a liter. Remember, 1,000 milliliters is the same as 1 liter, so this is still the correct molarity. Now, what goes in this second step? Well, that's right, the molar mass. So what you need to do is look up or calculate the molar mass of sodium bicarbonate. Sodium bicarbonate is NaHCO3. So if you want the molar mass for that, you have to add together sodium, hydrogen, carbon, and 3 oxygen atoms. When you do that, you get 88.007 grams per mole. If we plug all of this into the calculator, we get 0.937 grams. So if you got that right, great job. Let's go on to the next section, which is handling dilution calculations. Dilution is a really common task that we do in the lab all the time. It involves taking something that has a higher concentration to make a less concentrated solution by adding more of the solvent to it. So if we start here on the left where we have something called the stock solution, we can have a very concentrated solution with a very small volume. This is helpful for things like shipping and transporting and storage. Now, when we actually go to use it, we often have to dilute it to a more practical concentration. This involves adding more solvent to increase its volume. When we add more solvent, of course, we don't change the number of moles of the solute. We're only increasing the volume of the solvent. This therefore increases the volume of the solution and decreases the concentration. Now, it's very helpful when we're dealing with changing concentrations to distinguish between initial concentration and initial volume, or C1 and V1, and the final concentration and the final volume, or C2 and V2. Now, it turns out there's a very simple formula that we can use to help us with a lot of dilution calculations. It goes like this. The initial concentration times the initial volume, or C1 times V1, will have to be equal to the final concentration times the final volume, or C2 times V2. To see how this works, let's look at this example I have below. How many milliliters of a 12.1 molar solution of HCl are required to make 2,500 milliliters of a 3.00 molar HCl solution? So the first thing to notice is that this is a dilution problem. We're going from a more concentrated solution, 12.1 molar, to a less concentrated solution, 3.00 molar. We're seeing the molarity decrease. That's a dilution. And when we're doing dilution problems, we should use this formula, C1 times V1 is equal to C2 times V2. Now, in order to use it properly, it's helpful to keep organized what is the initial concentration and initial volume versus the final concentration and the final volume. So let's do this a lot like we do the gas law problems. Let's write down C1, V1, and C2, V2 from the information we're given in this problem. So when we read through it, make sure that we're looking for the initial conditions versus the final conditions. The initial conditions will have the 1 subscript and the final conditions will have the 2 subscript. So if you read through this, it looks like we start at 12.1 molar. So that's our initial concentration. So let's write that down. Reading through the rest of the problem, it says how many milliliters of this 12.1 molar solution are required to make, and then we're given the final sort of goal things that we're looking for. This is stuff at the end that we're trying to get to. So we see 2,500 milliliters. That's the second volume, or V2, and then we see the new concentration as well, which is 3.00 molar. So let's write those down for C2 and V2 as well. Now notice we're not told anything about V1. In fact, we're being asked how many milliliters of this initial concentration do we need. So let's put a question mark right there next to V1. That's what we are trying to solve for, and the equation we're using to solve it is this C1V1 equals C2V2. What we need to do is isolate that V1 variable and then plug in the values for C2V2 and C1. So notice when I put in my units for C2, V2, and C1, we get a canceling of the molarity unit, but the volume unit is left. And that's good because we're trying to solve for a volume unit. So once we plug all of this into our calculator, we get 620 milliliters. And that has two significant figures because notice my volume here, 2,500 milliliters, also only has two significant figures. So if we take 620 milliliters of a 12.1 molar solution and we dilute it all the way up to 2,500 milliliters, the new concentration will be 3 molar. So if you got that right, great job. Now I'm going to stop the lesson here. In the next lesson, we're going to do a few more dilution type calculation examples, and then we'll learn a few more things about solutions, colligative properties, and osmosis. So I hope you're doing well. Please let me know if you have any questions, and I will see you soon. Take care.